welcome. So in this lecture, we're going to be approximating the area under a curve using left endpoints. And in particular, we're going to look at this with an example. So our task is going to be to do an approximation for the function f of x equals x squared plus 1. We're on the interval -1 to 1.5, and we have 5 subintervals. So we'll start drawing the picture so that we can get a sense of what we're doing. So I'm going to start with, so I'm going to have my axes. So this is my x-axis and my y-axis, always good to label. Okay, and then I'm told I have from -1 to 1.5. -1 to 1.5. And then I'm going to have, I'm looking at the curve f of x equals x squared plus 1. Okay, so this is y equals x squared plus 1. And just to kind of remind yourself, what does it mean that this is the graph of f of x equals x squared plus 1? It means that a point on it is x, f of x, or in other words, to write this, we can write this as x, in this circumstance, x squared plus 1, just to give us a little bit of orientation as to what's going on. Okay? And so I'm looking at the area underneath it in this interval, but I'm going to divide it into 5 subintervals. So the first thing I need to do is to figure out, how do I divide this into 5 subintervals? Well, I'm going to take the entire length, and then I'm going to divide it by 5. So what's the entire length? Okay, so we're going to call this kind of this width of our subintervals delta x. So delta x is going to be the width of a subinterval. In fact, I want to do that in a different color. Okay, let's do that in blue here. Okay, so my delta x, which is the width of a subinterval, well, how do I compute that? Well, I'm going to take the difference between the two endpoints, right? I'm looking for this length here. How do I get that? I take this minus this. Hopefully you've seen that before. So I'm going to take 1.5, and then I'm going to take -1. But I said I wanted to divide it into 5 subintervals, so now I want to just divide that by 5. And if you take a few seconds to compute that, you should see that that's actually equal to 1/2 or 0.5. Okay? So over here, if that's my width, then how do I get the other endpoints of my intervals? Well, I just go through and I go, okay, well, I started with, blue I'm going to do it with. Okay, so I start with -1, I add 0.5, so here I get 1/2. I add 0.5, I get 0. I add 0.5, I get 1/2. I add 0.5, and I get 1. Okay, so now I've divided this up into 5 subintervals. But now what I want to do, and I'm going to use the same color as over there, just only have a limited number of colors, is I want to approximate this area using left endpoints. So I'm going to start at -1. I'm going to go up until I hit the graph. I'm going to go over to the end of my subinterval, and I'm going to go down. I'm going to call this area A1. Okay. Then I'm going to do the same thing for this subinterval. I'm going to start on the left-hand side up until I hit the graph, over and down. I'm going to call this A2. I do this again. On the left-hand side of this subinterval, I go up until I hit the graph, over and down. I call this A3. I look at this subinterval. I go up on the left until I hit the graph. I go over and down. I call this A4. On this subinterval here, I start on the left-hand side. I go up until I hit the graph, over, down, and this is A5. Okay. Well, now I need to actually, so if I want to approximate my area, I want to get to my approximate area. Well, what do? I just add together these areas. So I have A1 plus A2 plus A3 plus A4 plus A5. Okay. And now I need to think for a moment. So how do I know what this area is? Well, on the bottom part, right, down here, by exactly how I figured out my subintervals, this is my delta x. So this length here is delta x, right? And then keeping this in mind, how do I compute this height here? Well, I plug -1 in because the y coordinate is going to tell me f of x. So I put -1 into there. So this length is going to be f of -1 coming from my left-hand endpoint. Okay? So what I'm going to end up getting here is going to be, so this is going to equal, so I have f of -1 times delta x plus, now I do it for that, f of 1/2, that's my height for that subinterval, right? I'm looking at this height here. Again, my y value, which is my height, comes from evaluating f at that point. I keep on going. So I have f of 0 delta x plus f of 1/2 delta x plus f of 1 delta x. 1.5 never actually shows up as a left-hand endpoint. 1 shows up as a left-hand endpoint for that subinterval. So I stop there. And then I can go ahead and compute these, okay? Keeping in mind, so how when I have the graph of a function like that, how am I going to go ahead and do that? So I'm actually going to underline these to emphasize that these are that same function. Okay? So the way that I find useful is to go through, says x squared plus 1, put parentheses to replace the x, and then plus 1. Let's do all those first, and then we'll put in what we need to, leaving room for my delta x and my plus. So I've got 5 of these. I'm going to do this all very carefully. And in fact, here I can already notice, so I'm going to put in these values before I forget. So these are -1, and these are, oops, that should be a -1/2, -1/2, 0, 1/2, and 1. I could put delta x's in front of each of those, or I could make the observation that I can just pull it out because it's in front of each of them. I can pull it out in front. So my delta x is going to turn into a 1/2 here, and then I can put parentheses around the whole thing. Okay, so each of these can just be a plus. And then at this stage, so I can get 1/2 times 2 plus 5/4 plus 1 plus 5/4 plus 2, and that's going to equal 15/4. And then we have a name for this. Okay, so this is called, so we have L5. So L, because we're looking at left-hand endpoints. 5 comes from the 5 subintervals. Okay, so my answer is that L5, which is what I'm looking for, is 15/4. So that's my final answer. I one more time emphasize to you that this comes from the 5 subintervals. And the L there comes from the fact that I'm using the left endpoints. Okay. So what did we do here? So this should look a little familiar from before in terms of, right, remember when we talked about, I said it was kind of a warm-up to Riemann sums, so if I wanted to translate myself from a rate of change into a change of quantity, which is exactly what the integral is going to do, which is exactly the area under the curve, if I had a constant function, which I'm really doing here is I'm approximating this graph by a constant on its pieces, okay? Then we kind of know, just like we know that if I drive 3 miles per hour for 2 hours, then I've gone 3 halves. I've gone 3 times 2. I've gone 6 miles. Okay. Then we have a similar kind of thing here. I have my rate. It's constant. So if I want to know how much maybe my cost has changed over that time, if that's the rate of change of my cost, then I look at the rate, right, which is this, times the amount of time. So I've just broken this into pieces where I can use exactly that notion. And then I've gone through very carefully and actually computed it. Just doing those rectangles one at a time, with a key point remembering that what is a point on the graph of a function? It has your input x, and then your y, or your height, is actually your output of your function, okay, which here is our rate of change function, okay? So if I wanted to figure out the area of this rectangle, I'm taking my width, like my length of time, and I'm multiplying it by my height, which is actually my function evaluated at this left endpoint. Okay, and so once I computed that, I got the left-hand approximation with 5 intervals. And we'll do this also with the right hand, and then you're going to actually find that the integral, as we make these intervals smaller and smaller and smaller, so we're taking a limit, my integral is actually going to be the limit of, so I'm going to be able to integrate if the limit of the left endpoint approximations and right endpoint approximations are the same, then I'm going to be able to integrate, and in that circumstance, that's actually going to give me the area of the curve as I make my intervals very, 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 very small. So I hope this was helpful, and I will see you in the next lecture.